Let us now start with a question that must be answered. What is an electric circuit? Many of you will be fortunate enough to have some knowledge from school about some basics in electric circuits. I wasn't lucky enough to be taught it in grade 11 physics, yay COVID, but I was passionate about it anyways, so it didn't matter. Regardless, this very well may be the first time you've seen electric circuits. So let's start with an analogy that is often used for electricity: water. I will touch upon more water analogies where applicable, but beware that not everything can be represented by water analogies. After all, by the old adage, all models are wrong, but some models are useful. You can think of a circuit like a loop of pipe with a pump. We can put different kinds of things in the loop, and they can do different things. Say, we have a turbine in the middle of the loop. The loop can turn about and convert the linear kinetic energy of the flow into rotational kinetic energy that can be used in different applications, which is quite similar to a water wheel. As I've drawn here, you can notice that our rotational kinetic energy turns into some electrical energy and it flows the power lines. This is quite like what happens in a hydroelectric dam. We could also have something like a water tower, which suspends the water in a ball that is elevated. This way, we can store the energy from the pump for a later time, when the pump no longer runs. Notice how the water tower stores water and the level is maintained by the flow of the pump. This is similar to capacitors. For the sake of simplicity, we assume that the pipes have no losses and that they're ideal, that the flow does not slow down. Now, the main thing I want you to take away from this are threefold. Circuits must be closed loops to be useful. An open pipe and a water circuit is useless, i.e. it will leak. Circuits can have many different elements in them, which changes the circuit's characteristics. And lastly, circuits can experience losses through energy transfers and inefficiencies. Note that these all apply to electric circuits as well, and should be kept in mind going forward. Now, let's move on back to electric circuits, now that we are somewhat familiar with the overall concept of a circuit. To be a little bit more rigorous, I will provide you with my definition. Of course, it may vary from others' definitions, but so is life. A circuit comprises electrical components, or more accurately, representations, and wires that connect them. As I've mentioned before, these wires are magic wires. They are ideal. Components can include things like resistors, capacitors, inductors, operational amplifiers, diodes, LEDs, or light-emitting diodes, and so on and so forth. However, for this course, we are typically looking at the first four. The later components will be covered in 240 for ECE in general, and 340 for only EE. Now, some of you may ask, why do we even use symbols? What's up with them? We could technically use the actual real-life representations of some common components. In fact, if you use Tinkercad, you are indeed offered real-life representations of components in which you build your circuit, as if you are building it in real life. However, there is a severe flaw to this approach when analyzing circuits. Not all electrical components look like the above drawings. We can have wall sockets, a turbine, or even a black box. Even just a metal ball can be considered a capacitor. So instead, we use abstract symbols to represent sources, passive, and active components. I will clarify what those mean later. We use a circle outline to represent independent sources, a diamond outline to represent dependent sources, a zigzag line to represent resistors and any general resistance, 2 bars to represent capacitors or any general capacitance, a squiggly line to represent inductors or any general inductance, and finally, a triangle with positive and negative terminals to represent operational amplifiers. And there are all the symbols used in this course, though there are some variations that we will touch on later. Again, I will stress, these symbols are abstract. An ideal source is not the same thing as a physical device. Lastly, this is a question that I didn't know until way later, but the course is called linear circuits for a reason. The electrical circuits can be solved with linear equations, and thus linear equations are at play. So, it is a good idea to brush up on linear algebra for this course. That's all for this video. There are some more detailed things that I would like to touch on concerning independent and dependent sources, but that is outside the scope of this video, and instead will be in the next part, which will cover charge, voltage, and current.